Well, hello everyone. Mr. Goss here with section 3.4. The section 3.4 objective today, SWBA, students will be able to solve compound inequalities, section 3.4. Now you guys are watching this video obviously, and the nice part about this video is you guys can pause and rewind or even fast forward a little bit as you guys need. So you can go at your own pace here. So maybe you feel like I'm going a little too fast, okay, pause it and slow it back down. Or maybe you feel like I'm going too slow, taking too long at pauses. You can speed it up, or if it's just right, keep it there, okay? And you can always come up and ask me questions if you're watching this in class over this video. And you can always, at home, if you're watching it, or outside of my classroom, you can always email me or write down a question. Make sure you ask me it later, okay? And when you're done with the video, make sure to work on that worksheet for 3.4. If you don't have that already, by the time you're done with the video, make sure to come and grab that from me in the classroom or look on Google Classroom for it as well. Now, another tip is if you want to, while we're going through the practice problems in this section, if you want to pause at that point and then keep working and try it and then see what I do, that might be a good way to kind of check for your understanding, okay? But you don't have to. So let's start it this way. Compound inequality. So compound, we're putting multiple things together, okay? Is what compound means. So two inequalities that are connected by the word and or the word or. It's kind of weird to see or there. But they're inequalities connected by the word and or by the word or. So we have our and inequalities and we have our or inequalities here, and or. So for our and compound inequalities, when we see that, then the graph will be the intersection of the two graphs. So it's where they overlap. So it's where what the graphs share, where both of these inequalities are true. If I say it's this and this, I want both of them. Now we can write it in two ways. So like one of the ways could be that you say x is greater than 3 and, the word and, x is less than 5. Or you could also say, well, 3 would be less than x. So if x is greater than 3, you can also say 3 is less than x. And you can say that that number is less than 5. So you can say x is between 3 and 5, so to speak, instead of saying x is bigger than 3 or greater than 3 and x is less than 5. Whereas x is between 3 and 5 would really mean the same thing. In set notation, we'll write it in this format. We'll have our brace, x such that we put our smaller number less than x larger number. So just like here, where kind of the x is between the two. Now we have our OR graphs. For our OR graphs, the graph will be the union, we call it, the union of the two graphs. What's the union mean? Well, union is the solution of either inequality, but not necessarily both. We just care where there is a solution to at least one of the graphs. And let's practice this. We'll solve the inequality, graph the solution, write your final answer in set notation. So number one, we have x is less than negative 5 or x is greater than 1. So this is an OR graph, okay? Now, what we do for these is we solve these inequalities separately. So we solve x is less than negative 5 and our x is greater than 1. And these are actually both solved already. But later on, we'll have ones where we have to solve them. So right now, we would just end up graphing these. So we say, okay, on our graph here, I'm going to put negative 5 over here. I'm going to put 1 over here. And I know before we were putting multiple numbers kind of around the negative 5 and around the 1. But with these compound inequalities, we already have two numbers. So we already have an idea of what's kind of around negative 5. That, oh, 1 is to the right of it on this number line. And vice versa. Well, negative 5 is to the left of 1. So we're fine with it being that way. Now these would both be open circles. You do an open circle for this first one. X is less than negative 5. And x is less than negative 5 would be going up and to the left. And then if we graph x is greater than 1, it'd be an open circle there, and it'd be going to the right. Those are the numbers that are greater than 1. So if we put this into our set notation, I kind of put myself out of room here a bit, but if we put this into set notation, we'll see that we have, oh, I'm trying my brace here again. That was a really good one. I'm proud of that. X such that x is less than negative 5 or x is greater than 1. So we have our set notation, and our graph is saying, hey, anywhere over here is part of the solution, as well as over here. In between here, not part of the solution. This is not part of the solution because it's not where x is less than -5 or where x is 1 at. Neither of those things are true. But where I shaded blue, that is where it's true, where x is less than -5 or it's greater than -1. We don't necessarily care that it's both, it just has to be one of them. On the second one, we have x is less than 3 and x is greater than -3. So we'll graph these. So we're going to draw our graph again. I'm going to put two numbers on here. For my compound inequalities, I'm only putting 2 numbers on. Before we put 3, I'm not going to put 2, and it's only going to be the 2 we have our inequalities at. So -3 and 3. So it doesn't matter which one I graph first. I'll graph the -3 first. X is greater than -3. Okay? Greater than or equal to. So it's going to be a closed circle, and it's going to go to the right. Now before I keep going all the way to the right, I'm going to do something first. I'm going to start graphing my next one. X is less than 3. It's going to be an open circle. Less than 3 is going to go this way. So I didn't draw my arrow because it doesn't go all the way to the left because we're doing and. We just want where both of these are true. So both x is greater than 3, or excuse me, s is less than 3, and x is greater than or equal to -3 exists right here between these numbers. Anywhere between these two, and including -3, both of these inequalities are true. So then for our set notation, we would have x such that, and we said earlier we would do smaller number, so that is -3, is less than, in this case less than or equal to, because that's the symbol there, x, which is less than 3. So it's kind of like we end up flipping this inequality here. We end up flipping it and saying -3 is less than or equal to x. And so we write this inequality first down here. And then we go through and we write this inequality afterwards. And we just use 1x rather than writing x twice. This is what it kind of ends up being. And then that would be our answer. Continuing on to example 3. Example 3, we actually have to solve some of these. So we have an or in a compound inequality. And now we'd solve these separately. So 2a plus 1 is greater than 11. So we'd solve this by subtracting 1, subtracting 1. 2a is greater than 10. Now we divide by 2. And we're just completely ignoring this other inequality for the meantime. So we have a is greater than 5. Or, now we solve the second one. Well, I subtract 2, excuse me, not subtract 2. I subtract 2, or 3a. So -2a is greater than 2. Divided by -2. Because I divided by negative, I'll flip the sign. A is less than -1. So I have a is greater than 5 or a is less than -1. And so I'm going to graph this. I'm going to put my 2 numbers on here for my compound inequality, -1 and 5, because those are the 2 numbers we see. Once again, it doesn't really matter which one you graph first, but I'll graph the -1 first because I usually do the smaller number. It's going to be an open circle, and it's going to go to the left because those are numbers less than -1. For 5, it's going to be an open circle, and this one's going to go to the right. So, as we can see again, our OR graph is tending to go both arrows pointing to the outside. That's actually a pattern that we will see almost all the time, except for our special cases, which we will get into. So I will then draw my set notation for this. A such that. Now, you might be asking, Mr. Costa, does it matter which inequality we put first here for this OR one? And I'd say, well, let's do least to greatest just to keep it organized. Let's keep the smaller numbers first. That's a very common thing we do for organization is we do least to greatest. So I'll put A is less than -1 or A is greater than 5. You might also be asking, Mr. Costa, why aren't we putting these kind of together like we did in the last one? And I'd say, well, that's a great question, but we aren't doing it because of the fact that this is an OR graph, where we only do that with an AND graph because there's the overlap. So you end up kind of overlapping or combining those two x's in the middle. Number 4, 2x plus 1 is greater than -5, and 3x minus 1 is less than or equal to 11. So once again, we're really going to end up doing these separately. So I'll ignore the fact that the second one exists for a moment. So I'm going to subtract by 1. 2x is greater than negative 6, divided by 2. X is greater than negative 3. And add 1. 3x is less than or equal to 12, divided by 3. X is less than or equal to 4. So I'm going to graph this now. I'm going to put negative 3 on here, and I'm going to put 4 on here. Once again, it doesn't really matter which one we graph first. I'm going to do my smaller number, so I'm going to do x is greater than negative 3. This is going to be an open circle, and it's going to go to the right. Now, just like I did with my previous AND graph, I'm going to wait to draw the arrow. For my x is less than or equal to 4, I'm going to have a closed circle here, and it's going to go to left. And we'll end up seeing we actually don't need an arrow because the numbers over here are not part of the solution, and the numbers over here are not part of the solution, because for AND, we just want the overlap, which is going to exist right in between here, as well as positive 4, since it has a closed circle. So for our set notation, x such that, and this is where we end up flipping the small one. So instead of x is greater than negative 3, I'll have negative 3 is less than x. And we kind of then write the second part, the second one, the bigger one. X is greater than, or excuse me, x is less than or equal to 4. So it's where both of these are true. It's where it's in between it. Now you might be noticing ANDs are tending to go toward each other, and ORs are tending to go apart. That's going to be a very, very common theme for us and can be a way to help us check to make sure we're doing it right. Now sometimes that won't apply, but almost all the time it will. And like I said, we'll talk about in a bit when it doesn't apply. Now number 5, this looks written differently. Negative 3 is less than or equal to p minus 5, which is less than 5. Or is less than 2, excuse me. We don't see an AND or an OR, but we see two inequalities. So it's still a compound inequality, but which one is it? Well, it's written like how we wrote the end of our previous one with our AND. So this is really actually the same thing as negative 3 is less than or equal to p minus 5, and p minus 5 is less than 2. So we have two ways we can solve this. We can solve it by, if we look over here on the right hand side, I'll solve the blue one first, okay? So this one I would solve them separately again. I'd add 5, I get 2 is less than or equal to p. And add 5, I'd have p is less than 7. So we can end up solving it like that. Now the other way I can solve it is I can actually solve it over here. I'll do this in pink to make it look a little bit different. If I add 5 here, the question becomes, well, where do I add 5? Well, I actually have to add 5 to both the left and the right. So I'd do negative 3 plus 5 is 2, is less than or equal to p, is less than 7. And we really end up getting the same exact thing we got in the red there, except for here the p's are still smushed together, and in the red, we end up seeing the and between them and the p separated. But like we've been talking about, they really actually mean the same thing, like we saw in examples 2 and 4. So either way you do it is fine by me, but the big concern I have with problems like number 5 is that a lot of times I will see a student add 5 in the middle and then add 5 to either the left or the right, but they pick and choose. You can't pick and choose with these. You have to do it to everywhere we see an inequality symbol. So if you see an inequality here, you have to do it to the left and the right. If you see an inequality here, you have to do it to both the left and the right. So we did it to the left, the middle, and the right. You have to do it to all 3 parts here for a compound. So sometimes it is easier for students to separate it out like I did, the blue and then the red. Either way, we can graph these the same. The two numbers all right are 2 and 7. 2 will have a closed circle, 7 will have an open circle. Now this is an AND one, so that's a big hint that they're going to meet in the middle. But if you need to, flip the 2 is less than or equal to p around and say p is greater than or equal to 2 to see that it's going to go to the right, you definitely can do that. But here we actually don't have to, because when we have our set notation here at the end, we have p such that 2 is less than or equal to p is less than 7. We're supposed to write it like this at the end. We don't need to flip it around because we don't need it that way at the end. Whereas before, when we're doing just a single inequality, we need to flip it. But when we're doing a compound one, we actually don't in this case because it's the AND one. Let's go on to number 6. A plus 1 is less than 4, or a minus 1 is greater than or equal to 3. So we see here two different inequalities. We're going to have to solve them separately. And a good thing for us to remember is since it's or, we should think, okay, they should end up going different directions for the arrows at the end. The end one, both of them went inside. These should both go toward the outside. Let's try it out. So this first one, I subtract 1 from both sides. I get a is less than 3. Or, well, the second one, if I add 1 to both sides, I get a is greater than or equal to 4. Okay, now let's graph it. Two things I'm going to graph are 3 as well as 4. 3 will have an open circle, and it goes to the left because those numbers are less than 3. 4 will have a closed circle, and it will go to the right because the number is greater than 4. And as we see here, it does end up going opposite directions like we guessed it would have. And that's what it should do. So it's not that you should force it to go that way, but this is kind of a way to check it. It's like, it should go this way. It did go that way. That's good. Now our set notation, a such that, and we always try to put our lower number first here. Just keep at least the greatest to organize it. A is less than 3, or a is greater than or equal to 4. Now you might be wondering, maybe you're not, but hey, Mr. Kossel, so you just said on the previous one that we didn't need to flip this around earlier, this 2 is less than or equal to p. Would it be okay if I had 3 is greater than a? And I would actually say no, we still want those to be that same way with the a on the left-hand side, the variable on the left-hand side, when we're doing our ors, okay? The only reason that a problem like number 5 was a special exception was because for when we write it in set notation, we actually write it where it's all in one, and we don't even write the word and. We just know that this means that it's and, that it's between the two. Continuing on, write an inequality and solve. 2 times a number plus 1 is greater than 5 and less than 7. So 2 times a number plus 1 is greater than 5 and less than 7. So let's start here. 2 times a number. Well, 2x plus 1, so plus 1, is greater than 5. Okay, now we can write this one of two ways, and I'll show you both ways. So we can write is greater than 5 and 2 times the number plus 1 is less than 7. Now the other way we can write this out, it'll kind of look similar to each other, so I try to change them a bit. The other way we can write this out, I'll do it in orange, is we could do kind of combining them. So we can say if 2x plus 1 is greater than 5, then 5 is less than it. And we can say that's less than 7. And notice this is an and inequality. So we can write it like this. We can say, hey, 2 times the number plus 1 is greater than 5, and it's also less than 7 by rewriting it. Or we can put it all in a compound. Either way is fine. Now we were asked to solve it, so I'm going to solve both of these. On the far left, we subtract 1, 2x is greater than 5, 2x is greater than 4, man, I was missaying stuff, divided by 2, x is greater than 2, and subtract 1, 2x is less than 6, divided by 2, x is less than 3. So we end up getting x is greater than 2, and x is less than 3, which we can rewrite as 2 is less than x, which is less than 3. So x is between the two. And we can put x such that and call it our set notation here. Now to solve the one on the far right, we end up doing the same thing. We subtract 1. We subtract 1 to the left and the right as well. So we have 4 is less than 2x less than 6. Divide by 2 in the middle, but also on the left and the right. So we end up getting 2 is less than x, which is less than 3, which is the same exact thing. And we could also put that in our set notation. For our graph for this, we have 2, we have 3, they're both open circles, and they end up pointing toward the middle. Gives us an and one, as well as the ones greater than 2 are to the right, and the ones less than 3 are to the left. So our answer is that set notation as well as the graph. In this one, there's only one way to write it, because it's an or one. A number minus 1 is at most 9, or 2 times that number is at least 24. So let's start left to right. A number minus 1, so x minus 1, is at most 9. Well, if we look back in our section, or if you just remember, the at most means less than or equal to, saying, hey, that's the highest it can be is whatever's on the right, but it can be less than that. So x minus 1 is less than or equal to 9. Or 2 times the number, so the same number, 2 times x, is at least, so greater than or equal to, 24. Now we know 25 is funnier though, but we'll continue on with 24. And yes, I do make those jokes even in my videos. So now we'd end up solving them. So we solve these separately, add 1, x is less than or equal to 10. Or divide by 2, x is greater than or equal to 12. So let's graph these. I'm going to graph 10, I'm going to graph 12. 10 is going to be a closed circle, and so is 12, by the way, in case you want to do that. 10 is going to go to the left, and 12 is going to go to the right. So the or ones should go to the outside, and they do. And our set notation is x such that x is less than or equal to 10, or x is greater than or equal to 12. Continuing on here to our special cases. So sometimes it'll be helpful to make a rough draft graph and then a final draft graph, okay? So our first graph that we see here, we see each of these, we have 2 graphs. The first one's gonna be rough, the second one's gonna be final. Once again, these are gonna be start out as some normal cases, and then we're gonna see some special cases, okay? So this first one's a normal one. X is greater than 3, so 3x is greater than it. 5, x is less than 5. So 5 is open circle again, and x is less than it. But it's and, so we want the overlap. So for our final draft, we say, okay, we want 3, we want 5, open circles, and we just want the overlap. So we don't want those arrows on the end, because that's not overlap. So the bottom would be our final draft. This next one's going to be a little bit different, though. We notice it's the same thing. X is greater than 3, and x is less than 5, but it's or this time. That's going to change the world. So our rough draft actually ends up looking the same, because our rough draft, we're just graphing what we see. So we have 3, we have 5, they're both open circles, and we know 3 goes to the right, and 5 goes to the left. Now for or, we went where just one, at least one of them are true. Well, if we look at this, we see at least one is true over here, but there's at least one true over here too. So or really end up covers the whole thing. So we actually have 3 and 5, every single number covered, which means there's IMS, infinitely many solutions. So when it's or, and they end up going toward each other, you have IMS. So we had an or graph that went toward each other, which breaks the norm. Okay, this was the exception I talked about earlier. So we had an or graph go toward each other, and now it's IMS. Number 3 special case, we have x is less than 3 and x is greater than 5. So we flipped the inequality symbols from what we did before, from 1 and 2, and we have and again. So we have 3, we have 5, open circles at both. X is less than 3, that's going to be the numbers to the left. X is greater than 5, those are going to be the numbers to the right. Now wait, this is this is an and graph, and they're going away from each other. But we're looking for the overlap. So we ask ourselves, is there any overlap here? And the answer is no. There is no overlap here, so there is no solution to this one. So for compound inequalities, when you have an and graph go the opposite direction, both going out, it's a no solution. When you have an or graph with both going in toward the middle, it's an IMS, infinitely many solutions. Let's look at number 4. X is less than 3, or x is greater than 5. So we have the same numbers and inequalities as we did on number 3, but this time we have or instead of and. So let's graph them again, just like we did on number 3. And we say, okay, well, that's pretty normal for an OR graph. That's pretty normal for an OR graph. And so we actually just end up saying, we're going to keep the same exact thing. We don't need to make any adjustments for our rough draft, from our rough draft to our new one. And we're just going to have our same set notation of x such that x is less than 3 or x is greater than 5. We're saying, yeah, what was there is okay with us. So 1 and 3 were kind of business as normal. We saw 2 and 3 were our special cases. Okay, we're going to see kind of similar things going on here on 5 and 6 though. So we have x is less than 3 and x is less than 5. And we have the same thing on number 6 except for it's or. So on 5 with the and, we're going to graph them with a rough draft. So we got 3, open circle, and it's going to the left. 5, open circle, also going to the left. Now these are both going the same direction. They're both going to the left. And we want the and. We want the overlap. Well, do they overlap here? No. Do they overlap here? Nope. Do they overlap over here? Yes. So where's our overlap? Well, it's anywhere to the left of 3. That's where both of them are true. So at the end of the day, we just want x such that, or x so it is, less than 3. That's what we're concerned about. We're concerned about that x is less than 3. So because it was an and graph, we just want to look for the overlap. And once again, a special case is when this kind of stuff happens. This is not the norm. Okay, this is not the norm. I'm just walking you through multiple special cases. So we say, well, the and is just where both of them are true, which is only when it's less than 3. Let's look at this next one. We have the same rough draft here because it's still x is less than 3 as well as x is greater than or less than 5, but this one's or this time. Rough draft will look the same. 3 open circle going to left, 5 open circle also going to left. Now for or, we just want where one of them are true. So is one of them true here? Yep. Is one of them true here? Also yes. Is one of them true over here? No. So we just want where at least one of them is true. And in this case, it's anywhere to the left of 5. So we don't really care that we added in that less than 3 part because it's true whenever it's less than 5. Because if it's less than 5, or excuse me, if it's less than 3, then it's automatically less than 5. So our set notation would be just x such that x is less than 5. As long as it's less than 5, it's going to meet the criteria for hitting the or, because or it only needs one of them to be true, whereas the and needed both. On 7, once again we see the same inequalities between 7 and 8. We have x is greater than 3 and x is greater than 5, whereas on 8 we have x is greater than 3 or x is greater than 5. So and, we're going to do a rough draft, 3, open circle, and we're going to the right this time. 5, open circle, also going to the right. So it's going to be a very similar thing on number 5 as we had on number 5. It's not true over here, it's only true for one over here, but it's true for both over here. So that's what we're concerned about. We want where both are true. So both are true to the right of 5. So it's true when we have x such that x is greater than 5. That is when it's true for and when the intersection of the two graphs, the overlap of the two graphs. Let's look at number 8. This special case, once again, these are all special cases, not the norm. We're going to have the same rough draft here because it's the same inequalities, except for now it's or. So 3 open circle going to the right, 5 open circle going to the right. The OR graph is going to be very much so like number 6. We're saying, okay, well, neither of them are true here. Both of them are true here, but the whole thing is true here. So even just one of them, at least one of them is true anywhere from 3 and to the right. So for the OR, we just need where at least one of them is true. And so we're not concerned that we have to be greater than 5 because one of them is true as long as it's greater than 3. So x such that x is greater than 3 would make it so that at least one of them is true. Now, once again, if you guys have any questions over any of this, you guys can feel free to ask me. And if you haven't gotten your worksheet yet, please come up and grab it now. Otherwise, look on Google Classroom for it, okay? And we will have this done for next class on Wednesday when we're wearing pink, okay? On the 14th. Have a great day.